Okay, what I'll be doing in this video is talking about the in vogue topic of inverse functions, and you can bet that this will appear on a VCAR methods exam, and you can bet it's going to be a high-end question as well. They use inverse functions often as the basis of the very last question of the second exam. So let's go through what an inverse function is. So the reason we looked at one-to-one functions was so that we can create a new function, an inverse function, called the inverse of f. So the inverse function is denoted by f negative 1, and that's the inverse of f. Now, let's just do something that seems a little bit random, but we've got a set of ordered pairs, and that's a function. Those coordinates there are a function because for any x value, I get one y value, not two. Points are plotted right. What we're going to do is just swap the x and y coordinates of each point and plot the points. And what do we notice? So the first coordinate is going to swap to that. Then we're going to get 4, 3, negative 1, 5, negative 7, 6, and 6, 0. So let's plot those points. So here is 2, 1. Here is 4, 3, 1, 2, 3. There it is there. Negative 1, 5. Negative 1, 5 is there. And negative 7, 6 is all the way up there. And 6, 0 is there. Okay, now, do we notice anything? Okay, well, maybe they just look like a random scatter of dots, but what I'm going to do is rule this line or draw this line here, the function y equals x. So let's just draw that line in. And now what do we notice? Well, hopefully you can see that, and I'm just going to change my pen color here to, let's go this pinky purple. All right, those two there are reflections. They're a reflection. Ooh, they're a reflection. They're a reflection. And they are a reflection, okay? And hopefully then geometrically you will notice that to obtain the inverse function from the original function, the graph of f is to be reflected along the line y equals x, okay? And the following statements are true. So what you'll notice here is the domain of this function here, the original function is 1, 3, 5, 6, 0. And what will happen is because we swap the x's and y's, this domain will become the range of the inverse. So notice how the range, the y values that it can produce, are the domain of the original, and vice versa. These values here that are the range will all be sitting in the domain position. So what happens is basically the domains and ranges swap. Okay, so the domain of the inverse function is the range of the original. The range of the inverse function is the domain of the original. Okay, now you might be thinking, or maybe you're not, but I'll just go through it anyway. But you might be wondering why an inverse function requires a one-to-one function. So what I'm going to draw is y equals x squared. Right, now this is not a one-to-one function because it fails the horizontal line test. We get two of the same y value. Okay, it is a function, but it's not a one-to-one function. Now what I'm going to do is GeoGebra has got a thing called invert, and what we'll do is invert a relation and to produce the inverse of that. Okay, so it'll essentially swap the x's and y's. All right, and have a look at what happens. So invert f of x, please. All right, and interestingly, what it does is it produces this graph here. Okay, notice how it doesn't swap everything, and what it basically says is, okay, to produce g of x, which is a function, I can't include this bottom part here. I can't include that there, okay? So what it does is it only takes this part of the original, i.e. it makes it one-to-one by removing this part here so that it will produce that in return, okay? So that's why it has to be a one-to-one function, is because when it gets inversed, say for argument's sake, I did a true swap of x and y, and I had a parabola, then what it will become is something like that, which is not a function because it produces, for this, the one x value, it produces two y values. So that function there, although it is a function, is not one-to-one. We say that it's not invertible in its current state. We can restrict the domain to make it invertible though, to make it one-to-one. Right, so to inverse, the function must be one-to-one, otherwise it will not produce an inverse function. All right, so if I stick x into this function, 5 comes out. If I stick 3 into the function, 7 comes out. And if I stick 8 into the function, -10 comes out. So this is the original. This is what happens with f of x. Now we're looking at f -1 of x. Okay, this is the inverse function. What they want us to do is find or stick 5 into the inverse function. What will come out? Well, what will happen is that these swap, so that we swap x and y. So if 5 goes in and it's the inverse, then 1 has to come out, okay, the swapped x and y values. If 7 goes into the inverse, I'm just doing this one here, then what will happen is 3 will pop out. And finally, if -10 goes in, 8 will pop out, because what happens to an original function to produce the inverse function is x and y are swapped. Okay, so let's start having a look at this situation here. So we've got this function here, f of x on 3 all squared, and what we want to do is inverse it. So we're going to just start with let y equal f of x equal x squared over 9. And for the inverse, what we do is we need to include this line, swap x and y. Okay, we can't just swap them over, we need to explain what we're doing. Okay, so swap x and y, that means that y is going to become x and x is going to become y squared over 9. Y squared is equal to 9x. Y is equal to plus or minus 3 root x. Okay, so I'm rooting the 9 and rooting the x. So root 9 is just 3, root x is just root x, and because I've rooted both sides, it's plus or minus. Now here's an interesting problem here. Okay, so which one do we accept? Do we accept both of them? Of course not. Okay, because y equals 3x is actually that. Okay, and that is not a function. So how do we know what to do? Well, these questions should always start with you listing the range and domain of the original and the inverse. So let's do it. The domain of f is going to be 3, 6. We know that from the function. The range of the function, now how are we going to know what the range is going to be? Why don't we just do a quick sketch? So if I put 3 in, that's going to be 1, 1 squared is 1. When I put 6 in, it's going to be 2 squared, which is 4. 6, 4. All right, so that's going to be what we're looking at. Okay, so the range is going to be 1, 4. Now that means the domain of my inverse is going to be 1, 4, because when I swap x and y, what will happen is the range of the original function becomes the domain of the inverse. Now the range of the inverse is simply going to be the domain of the original. Okay, so now what to do here? Well, let's imagine this along the line here. What happens is when I mirror it, it's going to produce that, the top half of the square root, okay? That's actually what I'm after here, okay, is the top half, okay? Now, the other thing I know is that the range of the inverse function has to be 3 to 6, okay? So it has to be 3 to 6. It's going to be these values here, not the lower ones, not the ones below. Okay, so what I'm going to say is, but y equals 3 root x as range of the inverse function is 1 comma 4. So it's because of the range that I'm accepting the positive solution. And now that I've done that, let's strut our stuff and write this in full function notation. So its domain, I know, of the inverse is 1 comma 4, maps to the codomain set of all real numbers. F negative 1 of x, the inverse function, is 3 root x. Okay, so that's possibly a 3 to 4 mark question, 3 marks at least, to do all of this work. Okay, all right, let's go with this second problem. Find the inverse of this function here. So let's quickly sketch it up. We've got turning point of 1, 4, and it goes from 1 to infinity. It's going to look like that. All right, let's write our domain of a function is going to be as listed, 1 to infinity. The range of the function is going to be 4 to infinity. Okay, these y values up here. Okay, so the domain of my inverse function is simply going to be the range of the original function because I'm going to swap them. And the range of the inverse will be the domain of my original. Okay, we're all set. Let y equal f of x equal x take 1 all squared plus 4. Swap x and y, must include this line to explain kind of what you're doing. Apparently a few years ago, VCAR examiners on this question here, if you didn't write this line here, they pinned you on it. So yeah, let's just make sure that we're doing this. X equals x take 1 squared plus 4. My bad, that should be y. Okay, so I've swapped the x and the y values for the inverse function. Now I'm going to say x take 4 equals y take 1 all squared. Y take 1 equals root plus or minus x take 4, y equals rather, plus or minus root x take 4 plus 1. Okay, it's decision time. Okay, so now what we need to do is work out which one we accept, the plus or the minus. Okay, now what we're noting here is my range of my inverse function is going to be 1 to infinity. Okay, now remember this is the root function, move 4 across and 1 up. And which one do I want? Do I want the top half or the bottom half of the root function? Well, the range is 1 to infinity. That's this part here, it's the top half. So we're going to say, but y equals root x take 4 plus 1 as range of the inverse function is 1 to infinity. So that's why I'm taking the positive solution, okay, is because its range is going to be 1 to infinity. Then we're going to say f negative 1 such that the domain is 4 to infinity. Mapping to the codomain in methods, it's always the set of all real numbers. F negative 1 x equals root x take 4 plus 1. So again, 3 mark question there. All right, here we go with another inverse problem. It's another parabola. And this parabola is negative 4. And it's from negative 9 to 0. So negative 9 goes in, which is 81. 81 take 4 is 77. Okay, and that's included. So what's going to happen is it's going to come down to this turning point here. Okay, now the scale is way off there. Okay, but this graph here just serves the purpose of saying the domain of my function is negative 9 to 0. The range of my function, according to my graph over there to the right, is negative 4 to 77. Okay, that means the domain of my inverse function is going to be the range of the original. So this goes over the domain of -4 to 77. And the range of my inverse function is going to be the domain -9 to 0. Okay, let's get to work. Let y equal f of x equals x squared take 4, swap x and y for the inverse, x equals y squared take 4, x plus 4 equals y squared, y equals plus or minus root x plus 4. Okay, so what's that? That's the root function. It's moved -4 over, and that's what we've got. That's not a function. So what we need to do is restrict the domain. Okay, we need to choose either the top half or the bottom half. Okay, now note here that the range of the inverse function, the set of y values that can possibly come out of it, are -9 to 0. That's like down here. Okay, so this is a situation where we want the bottom half. Okay, so what we're going to say is y is actually equal to negative root x plus 4 as the range of the inverse function is -9 to 0. Right, let's start our stuff. F -1 such that domain -4 to 77 maps to the codomain all reals f -1 x equals negative root x plus 4. Okay, all right, let's go up against the VCAR question here. All right, so this would be tech active, but easily doable without, I believe. So what this is the root function, and its inverse function of this original function is going to be one of these functions. So that's the root function. It moves 2 units over. So that's what it's going to look like. Okay. Now again, that's tricky with the -4 there. A lot of you will think that that moves 4 units over, but the lowest value that this function can root is 0. So we say 2x take 4 equals 0, 2x equals 4, x equals 2. This is the lowest value that I'm allowed to put into it, and the values will increase from 2. So those x values increasing from 2 will still be accepted. Okay. All right, so there's my function. So its domain is 2 to infinity. Its range of the original function is going to be 0 to infinity. So we can actually quickly see that these are the 3 options. This is junk. This is junk because, why do I know? The range of the original function is 0 to infinity, which means that the inverse function is going to have a domain of 0 to infinity. 0 to infinity, 0 to infinity, and 0 to infinity. So all we need to do now is to swap x and y, and because this is multiple choice, it doesn't really matter what I write down here, and so syntactically I don't worry whether it's completely correct. So I'm just going to say that g of x, which is y, swaps to x, root, and this x swaps to y, 2y take 4. I'm going to square both sides, 2y take 4, x squared plus 4 over 2 equals y. It's that one. All right, bit of graphing. Sketch the graph of this hyperbola, coordinates as axial intercepts, and equations of asymptotes. All right, so asymptotes at x equals -2 and y equals 1. Okay, so we're going to get a y-intercept somewhere over here and an x-intercept somewhere over here. So y-intercept occurs when x is equal to 0, which is a half plus 1 equals 3 on 2. So the y-intercept is at 3 on 2. So it's going to be there. And the x-intercept occurs when y is equal to 0. X is equal to -3. There. Right, now I'm going to make my apologies in advance here that this is really hard to do with the equipment that I've got here. So my hyperbola is going to be absolutely awful, okay? But let's give it our best shot and see if I can draw something half decent. All right, that's not great, okay? That correction there can't be done. You've got to make sure that you rub that out, okay, on your papers. Whee, that is shocking. Okay, here we go. Better. That's not bad. Okay, so there is my hyperbola. State the domain and range of f of x. So the dom f is going to be all reals, not including -2. The ran of f, the range of f, is not going to include the 1. Okay, let's grab the inverse function. Okay, so the function is y equals 1 over x plus 2 plus 1. I'm just going to write it down here. Y equals 1 over x plus 2 plus 1. I'm just going to triple check that. X plus 2 plus 1. Okay, so what we're going to do is say swap x and y. X is equal to 1 over y plus 2 plus 1. Okay, x take 1 equals 1 over y plus 2. X take 1, y plus 2 equals 1. Y plus 2 equals 1 over x take 1. Y equals 1 over x take 1 take 2. So f negative 1 is a function such that it has a domain which is a set of all real numbers, not including 1. How do I know? Because the range of the original becomes the domain of the inverse, and also have a look at it. I'm not allowed to use x is equal to 1 because it causes a divide by 0 error. F negative, yep, not an equal sign yet, maps to the codomain, which is a set of all real numbers. F negative 1 x equals 1 over x take 1 take 2. Let's get to the inverse function on the graph paper on the previous page. Oof, this is going to get a bit messy. Okay, I'm just going to change pen color here. What do you reckon? Blue, sky blue, blue. Let's just use blue. Okay. Now my inverse function is going to be y equals 1 over x take 1 take 2. 1 over x take 1 take 2. Let's just triple check that. Okay. All right, so here we go. We've got an asymptote at x equals 1. And y equals -2. Now notice something about the asymptotes of the inverse function compared to the original. If you tell me that the asymptotes have swapped as well, yes, very good pickup. Look at that. X equals 1 for the inverse, that's the asymptote, y equals 1. So everything swaps basically, all right? Now, what's going to happen? We've got a positive, so it's going to go like this. So we're going to get an x-intercept somewhere here, I presume, okay, and a y-intercept somewhere down here, okay. Right, so let's get the y-intercept first. It's going to be y equals 1 over -1, that's -1, take 2, y equals -3. Of course it is, okay. Now that's a bit stupid of me. Now I'll explain myself. So this is the x-intercept, that's got to become the y-intercept, because again, everything swaps, okay. So the y-intercept is going to be -3, so that's going to be here, and I can draw this now. And this, which was 3 on 2, the y-intercept, is going to become the x-intercept because, again, swap x and y. This is 1, this is 3 on 2. Okay, so it's going to go down through here and along here. Okay, what else do we want to do? State the domain and range of the inverse function. Well, I've already kind of done most of that. The domain of my inverse function is the set of all real numbers not including 1, and the range of my inverse function is going to be all reals not including -2. Find algebraically the points of intersection between the original function and its inverse. Okay, so this is interesting. All right, so what many of you will do is you'll do f-1 of x equals f of x. And you'll do something like this, 1 over x. So the original function was 1 over x plus 2 plus 1. And you'll let that equal the inverse, which was 1 over x take 1 take 2. Which is okay. But that's going to be a really hard one to process and try to solve for x. And I'll show you an easier way. All right, so when an inverse function is found, what happens is they'll always intersect along the line y equals x. So what I'm going to do is I'll just quickly draw that line y equals x. So there it is there, and you can see that these two, the pink and the blue function, intersect along that line. If I continue down here, you can see that there, okay? And I'll just show you with GeoGebra as well. Let's come up with another function. So I'm just going to plot, so function x squared, starting at 0, finishing at 9, for argument's sake. And what I'm going to do is invert it. Invert f of x. There's its, whoops, that's not the inverse. Invert f of x. There it is there. And note the intersection point is 1, 1. That's along the line y equals x. So the inverse will always intersect with a line, or at the line y equals x, with the original function. Which, if that's the case, here's a much easier way of doing this very last problem. Instead of doing this, why don't we just take either the inverse or the original function? I'm going to go with the original, which is 1 over x. What was the original? 1 over x plus 2 plus 1. 1 over x plus 2 plus 1. And I want to find out when it hits the line y equals x, because if it hits the line y equals x, it'll hit the inverse. All right, let's process this. 1 over x plus 2 equals x take 1. Multiply both sides by x plus 2. Um, 0 equals, let's expand this and subtract 1. X squared plus x take 2 take 1. 0 equals x squared plus x take 3. Now that is going to be a quadratic formula solve. I can just quickly see that that's not going to factorize. So here's my x values. So x equals negative b, which is -1, plus or minus the square root of b squared, 1, take away 4 times 1 times -3, all over 2a, which is 2. X equals -1 plus or minus, that's 13 on 2. Okay, so here's our x value, -1 plus root 13 on 2. There's the x value of the first point of intersection. The other one occurs at -1, take root 13 over 2, comma, comma. So now we need to find out what the y value is. So we need this y value and this value, which essentially means we need to substitute this into either this function or this function. But wait, there's an easy way to do this, because between you and me, I'm not putting -1 plus root 13 on 2 into the function, into this thing here, right? I'd have to substitute that, then do all the processing to find out what y is. Now, can you think of an easier way? Remember, what's happening is that a function will only intersect its inverse function along the line y equals x. Now, what's unique about the function y equals x? It means that for every x value you feed it, y is going to be exactly the same. So if x is 2, it won't surprise you that y will be 2. If y is 3, x will be 3. And if x is -1 plus root 13 on 2, here's a really cool thing. The y value, I bet you, will be exactly the same, okay? Because what it will do is intersect along the line y equals x. If it's this x value, then it's got to be this y value. And here it is here, 13 on 2. And if you think this is crazy, jump on your calculator, define this function here, and jam that point into the function, and I bet you that will pop out. Okay, so that is inverse functions, and what I'll get you to do is 5G, those are the questions there. Make sure you complete the Chapter 5 review along with the Chapter 3 review to make sure that you're ready for any form of assessment when we get back.